Hi, welcome to our next unit where we are going to cover kinetics. So we're going to study kinetics in two different levels, two different perspectives. So one being the macroscopic level. Again, macroscopic meaning what you can see with your eyes. And so at the macroscopic level, we're going to consider the rates at which chemical reactions occur. And we'll talk about how we determine the rate of a reaction in just a little bit. And then the other viewpoint or other kind of level that we will look at is the particulate level, submicroscopic level. So at the level of the particles that are involved in the reaction. So in this level, we're going to be concerned with the reaction mechanism or pathway, the steps that take place during the reaction. So what actually happens with the chemicals that are involved in the reaction. So let's talk about rate. So for anything, so we'll get to what rate means in a chemistry context, but for anything, what is rate? Some examples, or a good example of rate would be velocity. Velocity is a rate. What exactly is velocity? Think about the units for velocity and then think about what velocity is. Velocity is measured in meters per second. So velocity is change in distance over change in time. So for anything, a rate is change in something over time. A wage can be a rate. How much money you make per so many hours that you work. So change over time. Now, in the chemistry context, there's a couple different ways that we look at rates of reactions. Here's one. So the change in the amount of moles of a substance per liter per time, or just simply molarity per time. So change in molarity, change in the concentration of a substance over change in time. So remember, anytime you see the formula of a substance written in brackets, that means moles per liter. So the change in the amount of the substance in moles per liter, if it's a gas, or per liter of solution, if it's aqueous. So there's many different ways of determining the rate of a reaction, but again here, probably change in concentration over time is the most common. Pretty much anything that you can measure, though, we can use to determine the rate of a reaction. So besides concentration, what else could you measure about a chemical reaction, and what kind of change could you measure over time? Go ahead and pause the video and list some things. So hopefully you have some of these. Change in temperature over time. If you have an endothermic or exothermic reaction, you can measure the change in the temperature that occurs. Change in volume. If let's say you have some gaseous reactants or products involved in the reaction. Change in pressure. Change in absorbance. If we're using a spectrophotometer, we have a colored species involved in the reaction. And their change in mass, maybe, is another one. So there's lots of different things that we can measure the change of over time during a reaction. So let's take a look at this example. Now think about what this tells us about the reaction. So we have nitrogen and water reacting to produce ammonia and oxygen. Everything in this reaction is a gas. All right, so how can we measure the change in reaction? So again, reaction rate involves the time it takes for one of two things to happen. Either the reactants to disappear or for the products to appear. How long does it take for the reactants to disappear? How long does it take for the products to appear? So because the reactants' concentrations are decreasing, we're going to represent that with a negative, as you'll see here. So with respect to the nitrogen, let's write it like this. So again, we have delta, so change in nitrogen concentration over change in time. Put it as a negative because the change in concentration is going to be a negative, so minus and minus, we get a positive for the rate of reaction. Now, take a look at the water. Notice that the water is going to be produced at a rate consumed rather, at a rate 3 times that of the nitrogen. Meaning for every 1 mole of nitrogen that reacts, 3 moles of water reacts. So how do we want to have the same number here, even though we're using different substances to calculate the rate. So with respect to the change in concentration of the water, we're going to take negative 1/3, the change in concentration of water over change in time. So again, these two things here are equal because the water is being consumed 3 times faster than nitrogen. We'll take its change in concentration and divide it by 3, and that'll give us the rate of the reaction. How about the rate of the reaction relative to the production of ammonia? So again, products concentrations increase, so we're going to express this as a positive value. The ammonia is being produced twice as fast as the nitrogen is being consumed. Again, for every 1 mole of nitrogen that reacts, you produce 2 moles of ammonia. So we want to go change in concentration of the ammonia over change in time, multiply that by 1/2 or divide by 2, and that'll give us our rate of reaction. How about relative to how fast the oxygen is produced? Again, it's a product. So is it going to be, using these ratios, 2/3 or 3/2 times the concentration of oxygen? For every 2 moles of nitrogen that reacts, 3 moles of oxygen is produced. So oxygen is being produced 1.5 times faster than the nitrogen is being consumed. So we're going to multiply by 2/3. Let's see if I can squeeze this in there. So again, what's important to note is that all of these are the same number. They're all relative to each other based on the stoichiometry of the reaction, how fast the reactants are being consumed, how fast the products are being formed. All right, let's take a look at an example on page 610. Read along. It says, at some time we observe that the reaction 2N2O5 makes 4NO2 plus O2 is forming NO2 at a rate of 0.0072. I don't like doing the moles per liter second. Let's change that to molar per second, 0.0072 molar per second. Usually we don't use molar for gases. We're more likely to express our concentration in moles per liter. But again, moles per liter, same thing as molarity. So I'm just going to go with molar there. So we're given the rate at which the NO2 is being produced, 0.0072. What is the rate of change of oxygen at this same time? So notice that the oxygen is being produced 1/4 as fast as the NO2 is being produced. So you have 4 moles of NO2 produced for every 1 mole of O2 that's produced. So if you take a look at the solution at the top of the next page, we're going to multiply the rate of formation of NO2 by 1/4 or divided by 4 to get the rate of formation of the oxygen. Letter B, what is the rate of change of N2O5? So how fast is the N2O5 being consumed? Well, looking again at the equation, we say that the N2O5 is consumed at half the rates that the NO2 is being produced. Again, for every 1 mole of N2O5 that reacts, you make 2 moles of NO2. So the NO2 is being produced at a higher rates than the N2O5 is being consumed. And so again, this time we're going to take the rate of formation of NO2 divided by 2 or multiply by 1/2. And notice because N2O5 is a reactant, we're going to represent its change in concentration as a negative. So negative 0.0036 moles per liter second. And then letter C, what is the rate of the reaction at this time? So we can use any of these substances. And so the easiest one to use would be the one that there's just one of. So whatever there's one of in the equation, then that's the rate of the reaction. So we can look at oxygen. Oxygen is being produced at a rate of 0.0018 moles per liter second. All of these are the same though, if you notice. If we take half the change in concentration of the N2O5, we get 0.0018, or 1/4 the rates that the NO2 is being produced, 0.0018. They're all the same, kind of like what I was trying to show you before. All right, try one like that. Number 9 on page 651. Go ahead and pause the video. All right, so we're given the rate of the reaction. And again, this is because there's 1 mole of nitrogen involved in the reaction. This is also the rate of consumption of the nitrogen. And so we can use the rate of consumption of nitrogen to determine the rate of consumption of hydrogen and the rate of production of ammonia, just using the mole ratio from the chemical equation. So if the nitrogen's concentration is changing negative, because it's a reactant 0.3 molar per minute, then the hydrogen is reacting at a rate that's 3 times that. Remember, 1 mole of nitrogen reacts, 3 moles of hydrogen reacts. So that's negative 0.90 molar per minute. And then with respect to the formation of ammonia, ammonia is being produced twice as fast as the nitrogen is being consumed. Ammonia is a product, so we express the change in its concentration as a positive value, 0.60 molar per minute. All right, let's take a look at this equation. I want to show you graphically what's happening with the concentrations of each of the substances during the reaction. So go to page 609. And so what this graph shows is kind of what we just been talking about, the rate of consumption of the reactants, the rate of formation of the products. So ICl is a reactant, and so we see this change in concentration starts off with 2 moles per liter, and its concentration, of course, decreases because it's a reactant. Hydrogen's concentration, whoops, let's fix this in our notes here. Hydrogen's concentration is also decreasing, so we started with 1 mole per liter, and after some amount of time, after 1 second, it goes down to 0.674. The ICl goes down 1.348. And so we can see the change in concentration that occurs over time with that data. And so we see that the ICl is being consumed at a rate 2 times that of the H2. All right, figure 16.2 on the next page, again showing this graphically. So we have the red shows the change in concentrations of the reactants. They are decreasing. This is a very important graph to be able to analyze. And then the blue shows the change in concentrations of the products. Notice they start at 0. Their concentrations increase. They reach some maximum level. The reactants, their concentrations reach some minimum level. Not sure if this reaction did not go to completion, or perhaps we have a reaction occurring in a closed container where equilibrium is achieved. We'll talk about that later. Something important to notice is that the rates that the changes occur change. So if we look at, say, any one of the red lines, so look at the ICl. If we were to draw a tangent line at some particular time, that would give us something called the instantaneous rate, the rate of the reaction at some particular time, the rate of change of that substance at some particular time. And we can see that in the second graph. The initial rate can be found by drawing a tangent line at time 0. And as the reaction proceeds, the rate changes. Well, as the concentrations change, so does the rate. So we see different rates of change between the two substances, reactants, between the two reactants, and also between the two products. And we see that over time, the rate changes as well. So this type of curve lends itself well to differential equations. We are not going to do those in this class. But nevertheless, we can at least take the slope of a tangent line to determine either initial rate if at time 0 or instantaneous rate at some other time than time 0. All right, so we already talked about 16.3, so we're good there. All right, how about this? What has to happen in order for a reaction to occur? So going back to Chem 1, we said really 3 things, sort of 2, but 3 things need to happen for a reaction to occur. This is based on something called the collision theory. So first one there hopefully makes sense. In order for two particles to react, the particles must collide. Now be careful, not all collisions result in a chemical reaction. So the next two things in the notes are kind of the conditions for the collision to result in a reaction. Condition number one, the colliding particles must hit at the correct location or orientation or angle. Take a look on page 632. There's a really good diagram that shows this. So we have reaction between nitric oxide, NO, and nitrous oxide, N2O. Now in letter A, what it shows is the oxygen end of the N2O molecule colliding with the nitrogen end, so nitrogen's blue, oxygen's red, nitrogen of the NO. That is a collision that will result in a chemical reaction. Now take a look at letter B. What if you have the nitrogen from N2O colliding with nitrogen from NO? Those particles are just going to bounce off of each other and no reaction occurs. This is known as an ineffective collision, a collision that does not result in a chemical reaction. Now let's take a look at letter C. We have the nitrogen of the N2O molecule colliding with the oxygen of the NO molecule, but once again, that collision does not result in a chemical reaction. That is an ineffective collision. So that's what's meant by the particles must hit at the proper location or angle or orientation. Not only do they have to collide at the correct angle or orientation, but those particles must collide hard enough. So if the particles do not collide hard enough, again, they'll just bounce off of each other and we have an ineffective collision. So the particles must be moving fast enough in order for that collision to result in a reaction. And that's where activation energy comes into play. So of the two, which is more important, that the particles collide at the correct angle or that they collide hard enough? It is more important that particles collide hard than they collide at the correct location or orientation. So manipulating these three requirements will alter reaction rates, as we will see in the next section coming up.